Today we're going to look at systems of differential equations, differential operators, and we're going to look at qualitative understanding of nonlinear systems. So we're going to start with looking at non-homogeneous linear systems and solving for the critical point, and then understanding qualitatively what that phase portrait looks like. So we're going to classify that according to one of the 6 classifications, but we'll only look at that briefly. The main idea here is to be able to have some qualitative understanding of nonlinear systems when you can't necessarily solve them easily. Because remember, the best approaches that I know of would be to take a numerical approach and find a solution to your system numerically, and then connect all the dots and you find a plot of the picture, right? So since we're not doing that, the best we can do here in these very difficult problems is have a qualitative understanding of the nature of the critical points and use that to be able to predict the long-term behavior of an initial value problem in a difficult nonlinear system. Okay, so let's begin by looking at this non-homogeneous linear system. And it's not homogeneous because we don't have a plus 0 there. We have a plus minus 3, and down here we have a plus 4. So we can't write our matrix equation as y dash is equal to a times y, where a is a 2 by 2 matrix. We have this plus b here. And what that does is it just shifts over the position of the critical point. So let's have a look at this example here. So we have x dash is a linear equation, y dash is a linear equation. So we want to write this as a matrix equation. Now we can just read off the coefficients 2, 4, minus 1, minus 3 and put that in a 2 by 2 matrix. And then what's left over there is the minus 3 and the minus 4. We put that in a vector b. So we have y dash equals ay plus b. And now the critical points of this system, or the equilibrium solution, occurs when y dash is equal to 0. So what we need to do is solve the system ay plus b equals 0, 0, meaning that we take the b over to the right-hand side of that equation. And in this case, we've got 2, 4, minus 1, minus 3, y star, where the star means the critical point. Okay, so that's equal to minus b, which is 3 minus 4. So we can solve this by taking the inverse of that matrix. It's pretty easy. And then multiplying by the inverse of that matrix A. We do so on the left, so that clears the A on the left, and we just have y star. So y star is a half, 3, 4, minus 1, minus 2 times 3 minus 4. And we multiply that out, and we get minus 7 over 2, and then 5 over 2. Okay, so that is our critical point. That is where, in the phase portrait, that corresponds to the line in 3D, right? Remember, these phase portraits are projections of a 3-dimensional solution onto the x, y plane. Okay, so we found our critical point. Now we want to classify this, and we do so just in the same way as we did with homogeneous systems. So we calculate the trace and the determinant of the matrix A. In this case, the trace being the sum of the diagonal elements is 2 minus 3. Just look at these. 2 minus 3 gives minus 1, so that's our trace. The determinant of the matrix is 2 times minus 3, which is minus 6, and then minus 4. So minus 6 plus 4 is minus 2. Now that's negative. So if we look at the chart on the previous page in week 7, we'll see that we have a saddle. Let's have a look back here. We've got a negative determinant, so that's a saddle. The position of the saddle is not at 0, 0. It's shifted over because we have a non-homogeneous system. Okay, so the position is at the critical point. So let's have a look at the diagram now. So we see that we have a saddle, so a hyperbola within those asymptotes, which are the lines that we see. But you see there that the position is shifted over to the critical point. Okay, so it's very much like what we did for homogeneous linear systems. The only difference is that the critical point is not at 0, 0. It's somewhere else. And so you've got the extra step of finding the position of that critical point. All right, so let's have a look at another topic here. So Margaret's done a lot of this in her videos, but I'll touch on it here as well because it's another useful technique in solving systems of differential equations using using differential operators. So we've got an abbreviation here, d superscript n. So let's let that denote the differential operator d superscript n with respect to t. So this is just the operator that takes the nth derivative. All right, in other words, dy on dx would be the first derivative, d2y on dx squared is the second derivative, but setting this out as an operator that operates on y is rather convenient. So let's have a look at this. We'll start with this example here. Okay, and I'm going to annotate some more missing details here. So consider the system x dash plus y dash plus 2y equals 0 and x dash minus 3x minus 2y equals 0. So we want to replace the dashes with differential operators. So the differential operator d on dt in this case operates on x, and that gives us x dash. So we just put a d in front of the x. Likewise, for dy on dt, we just put d, then y. Okay, and we still have the rest of this. So we can write this as if we're factorizing out an algebraic expression. So that's what we're doing here. We're factoring out the y on the right-hand side, just like you would in algebra. Okay, and so we have the operator d plus 2 operating on y there. And likewise, in the second equation, we have the operator d minus 3 operating on x. Now, we want to solve this via elimination of one of the letters. Okay, so we do so by applying the differential operator d minus 3 to the first equation. All right, and now doing so gives us d minus 3x, then we have d minus 3, d plus 2 operating on y equals 0. And then in the second equation, we want to operate with d. So we apply d, and we get d minus 3 operating on x, minus 2, d operating on y. And the reason we did that is so that we can take a difference of these two equations and eliminate the x. Because you see we have d minus 3 of x and d minus 3 of x in each equation. So subtracting those two equations will give us an equation just involving y. Okay, now in the next line, I think I've probably skipped a few steps, so let's just do something here. Okay, so we want to expand this out now that we have this in terms of one letter. So we have d, two of the d's operating together gives us d2y, and then we have plus 2 dy, then we have minus 3 dy, then we have minus 3 times 2, minus 6y, and then plus 2 dy equals 0. Okay, so we've expanded this out. Next, what we want to do is collect like terms. So let's shift this over. And essentially this middle one is 4 dy minus 3 dy, which is just 1 dy. So we'll get rid of that part and we'll just put plus 1 dy, and then we still have the minus 6y. Okay, now let's replace the d2's and the d by dashes. So that says y double dash plus y dash minus 6, y is 0. All right, so now I'll go to double screen and go back to that. Okay, so we see how we obtain this second order linear system here. It is homogeneous, so we know what the solution to that looks like. We have y equals c1 e to the minus lambda 1 t plus c2 e to the lambda 2 t. So lambda 1 and lambda 2 are minus 3 and 2 respectively. So lambda 1 next to the t, lambda 2 next to the t there. Okay, so a similar process, eliminating y up here, will give us an equation in x. And similarly, we expand it out and replace the d2x with x double dash and the dx with x dash and so on. And we have an identical looking homogeneous second order equation. The solution to that looks very much the same. X is equal to c3, don't use the same constants, e to the minus 3t plus c4 e to the 2t. All right, so there's an alternative approach where what you would do back up here at the top is you would solve this system for x dash. You would solve the system for y dash, and just to give you an example, you could do so by subtracting the second equation from the first, which would eliminate x dash, and then you would get an expression for y dash. And likewise, let's see, so if you had an expression for y dash, you could back substitute into the first equation and get an expression for x dash. So that's what I've done here as an alternative approach. Then you could write this as a homogeneous linear system. You know that the critical point is 0, 0, because there's no plus b there. You take the trace of the matrix, 3 minus 4 is minus 1, and the determinant of the matrix is minus 12 minus minus 6, which is minus 6, and note that that's negative. So we get a saddle just looking at that stability chart. So the critical point at 0, 0 is a saddle, and therefore it's unstable. The eigenvalues of that system are minus 3 and 2 respectively, and so the corresponding eigenvectors are minus 1, 3 and minus 2, 1. So from that we get our general solution in terms of the vector y, which is x and y. So we have x is a e to the minus 3t times the vector minus 1. I don't know what I said before that, but so we've got this general solution. Okay, now remember what this phase portrait is. It's a two-dimensional projection of the three-dimensional trajectories onto the xy plane. And so that's what I'm trying to depict here in this second box on the right. So I've got some of those trajectories plotted in 3 dimensions, just in some little time range. So you can see each of these arrows corresponds to a trajectory where time goes back there, I think. All right, we can see the critical point here would correspond to a horizontal line. If you took this and rotated it to the side, you'd see a horizontal line. That is this critical point. It's an equilibrium solution. Okay, let's move on to the next section, linearization of nonlinear systems. So suppose we have a system of interconnected or coupled differential equations where the expression on the right of each of the equations is a nonlinear function. They can be tremendously difficult to solve. And so what we want to do here is look at what happens near the equilibrium solutions or the critical points to get an idea of the long-term behavior of the system given some initial condition. Like, for example, does it oscillate around some critical point, or does it just tend away? So these tools can tell you how that goes. All right, so what we want to do is linearize by taking what we call a Jacobian matrix. Now, I've got non-standard notation for that because I don't want to confuse with the D's of the previous section, and some people like to use an uppercase D for the Jacobian matrix. So I'm just putting a J subscript F. Notice I've got an uppercase F to be the vector function, FG. Okay, it's just the collection of those two functions in a vector. Okay, so J subscript uppercase F at the critical point. That's what the stars are for, critical point. So you've got to find the critical point before you go through this process, most likely. So basically, these are partial derivatives here. So we take the partial derivative of F with respect to X. We take the partial derivative of F with respect to Y. That's lowercase f. And then in the second row, we take the partial derivative of G with respect to X. And in the final entry, the partial derivative of G with respect to Y. And then once we have those, we sub in the critical point and we get a matrix with numbers in it. Right? So in other words, we get a linear system that behaves almost identical to the nonlinear system's critical point near that point. And so we'll be able to classify saddles, nodes, spirals, centers, and so on. Okay, so what we're going to get then is y dash equals the Jacobian matrix at the critical point times y plus some b, where b depends on the critical point x star y star. But how it actually depends, let's go back. Well, actually, I can talk about it here. Okay, so what you want to do is, it's the b, essentially, that gives you y dash equals 0 when you sub in the critical points. But we'll see an example of this coming up. So let's have a look at that example then. So the predator-prey model that we've already talked about. Okay, so we just described this system, or relationship between rabbits and foxes, or rabbits and wolves. So some prey, like rabbits, that reproduce at a particular rate, and some wolves which eat at a particular rate. And so they have a interconnected rate of change there. So x is the number of rabbits, y is the number of wolves. Suppose we have constants a is 6, b is 1, c is 2, and d is 4. Then we have the nonlinear system. X dash is 6x minus xy, and y dash is 2xy minus 4y. So we'll let f, lowercase f, be the top right-hand side, and lowercase g be the bottom right-hand side. And then we have the vector uppercase F is the collection of the two of those, F followed by G. So first we want the critical points of the system. So we've got to solve this nonlinear system here. Sometimes that's easy, but sometimes it's not easy. When it's not easy, you would use a numerical approach called Newton's method for solving nonlinear systems. You could look that up in your own time. We're not going to cover that. We're going to just solve nonlinear systems that happen to have easy critical point solutions. Okay, so we need to solve, in this case, the right-hand side equals 0. So here we have 6x star minus x star y star equals 0. And 2x star y star minus 4y star equals 0. Okay, so you could factorize the first equation there, factorizing out an x star. And then what you would have left is 6 minus y star in brackets times x star. And so you see that you must have either x star is equal to 0 or y star is equal to 6. okay, for that point to be critical. So you go down to the second equation. Now, with the second equation, you can factorize out, and I think probably I should just pull up the writing window so I can talk about this. Okay, so let's go through this. We have 6x star minus x star y star equals 0. Okay, so that's our first one. The second one is 2x star y star minus 4 y star equals 0. Okay, now let's factorize these. So I'll factorize the x star out of the first equation. And we'll factorize the y star out of the second equation. Okay, let's write. We must have x star is 0 or y star is 6. Let's say in front, from the first equation, we must have this. Okay, full stop. Let's make another sentence about the second equation. From the second equation, we must have, let's see, y star could be equal to 0, or this one here gives x star equals 2. Okay, so we combine those together. So if x star is 0, so let's write this out. So if x star is 0, then, well, clearly x star is not equal to 2 in that case. Then we must have y star is 0. So those two go together, and we have the critical point 0, 0. Okay, so that's one of them. So let's look at the next case. If y star equals 6, then we can see that y star is not 0. So we must have x star equals 2. Okay, so those go together. So 2, 6 is the only other critical point. We can see that there are only 2. All right, so given those, we know that there are 2 critical points. So what we want to do next is take the Jacobian matrix of uppercase F. So let's just carefully do this. So J subscript uppercase F is, it's a 2 by 2 matrix consisting of partial derivatives . So I'll fill in all the partial derivatives first, and then I'll sub in the x and the f and the g. Okay, the top row has f's in it, second row has g's in it. Okay, so we've got to calculate this. So let's sub these in now. Okay, so f was equal to 6 x minus xy and g was equal to 2xy minus 4y. All right, so simplifying the partial derivative of f with respect to x here, we can see that the derivative of 6x is just 6. And the derivative of minus xy with respect to x partially, remember we treat y as a constant, so we have minus y there. All right, so next, let's take the partial derivative of lowercase f with respect to y. So since x is treated as a constant there, the derivative of 6x with respect to y is just 0. And then the derivative of minus xy with respect to y is just minus x. All right, next we're differentiating g with respect to x partially. So the derivative of 2xy with respect to x partially is 2y. And the derivative of minus 4y with respect to x partially, remember we treat the y as a constant, so that's just plus 0. Okay, now the derivative of g with respect to y partially, so we start with the derivative of 2xy with respect to y partially, we get 2x, and then the derivative of minus 4y with respect to y is minus 4. And so we have our Jacobian matrix. Okay, so next we want to sub in the values of the critical points. So let's do 0, 0 first. So we're just replacing x with 0 and y with 0. And that's a very simple matrix. Most of the entries, well, 2 of the entries are 0, I believe. Okay, so we've got 6, 0, and then we have 0, and then we have minus 4. All right, now let's do the other one. So the Jacobian matrix at the critical point 2, 6 would have a sub in 2 and 6, so 6 for y and 2 for x. Okay, let's simplify this. 6 minus 6 is 0. 0 minus 2 is minus 2. Then down here we have 12. And then we have 4 minus 4 is 0. Okay, great. So we have the matrices for the linearized systems. So now let's write each of the linearized systems. So we have for the critical point 0, 0, so we have y dash equals this matrix 6, 0, 0, minus 4 by y, and then what's the b part of this is the two numbers that give us 0 for the derivative at the critical point. Okay, so if we replace the y by 0, 0, we just have 0, so we don't need a b. It's just, hang on, I want a vector, so it's just 0, 0 in this case, right, for that one. All right, now for the other one, we have something very similar, except this time we have the matrix 0, minus 2, 12, 0 times y, but this part of it is not 0, 0, it's 12 minus 24 because, hang on, I'll show you why in a second. So we'll just put in 12 minus 24 because when I sub in the critical point here, which is 2 and 6, and multiply that out, I've got minus 12 in the top row, and then I've got 2 times 12 is 24 in the bottom row. So this is what I need to take over to the other side. All right, so let's write that carefully. take this over to the other side of that equation. Hang on, I wanted 0, 0 there. Okay, so this gives us 0, 0, as in y dash equals 0, 0. All right, so that's why we have this particular b there. It's the thing that gives us 0, 0. So if you take that minus inside, all right, so let's do that as well, plus, and we change the signs of these, we get 0, 0 for that, which is our y dash of 0, 0, which makes that critical. All right, so let's write down, we've got our two linearized systems near those critical points. So now what we want to do is classify each of these. So in the top one, we have the trace of the matrix A is 6 minus 4 is 2, and the determinant of the matrix A is minus 24, which is negative. So this is a saddle near the critical point 0, 0. All right, now with the other one, we take the trace. So the trace of the matrix A is 0 plus 0, which is 0. And the determinant of the matrix A is 0 take minus 24 for 2 times 12, or minus 2 times 12. Okay, this is 24, that's positive, right? So since we have a positive determinant and it's on the axis, that's a center. Let's go back and have a look at chapter 7 here on the stability chart. Okay, we have a positive determinant, but it's on the determinant axis, right? Because the trace is 0. So those are centers there in the middle. So we've classified this as a center, so it's going to look like what we have here as our 6th classification, the centers. All right, so let's go ahead and have a look at what that looks like. So this is the actual phase portrait of the actual nonlinear system. So you can see around this, they're not quite ellipses, are they? They're closed circuits there, but they're not quite ellipses. As you get very close to that critical point, they look more like ellipses, right? So when you get close, it behaves like what the linearized system tells you. Okay, so that's the 0.26, which we classified as a center near the critical point. So we know that there is periodic behavior for initial conditions that are in this quadrant, essentially, right? Whereas at the critical point 0, 0, we worked out that the linearized system told us that this should be a saddle. So near it, it's a saddle. We see that, and there are no other critical points. So we know that all of the trajectories are governed by these two critical points, right? So for example, if you have an initial condition, initial value problem that starts in the top left quadrant, then you know that the trajectories tend down and away. They go out here, right? So in other words, you get x going negative and y staying positive. Okay, but remember, since this is a predator-prey model, we actually don't care about these 3 quadrants down here because they all correspond to extinctions, right? Because we must have x greater than 0 and y greater than 0. All right, so what it tells us is that all of our initial conditions are going to be in the top left quadrant, or sorry, the top right quadrant, and they're all going to oscillate around this critical point, right? So if you start with an initial condition here, you're going to follow a trajectory that's not quite elliptical, but it will oscillate around. And I'll just point out again that this is a projection of a 3-dimensional plot because you have an x, you have a y, and you have time, right? So what this will model is the quantity of rabbits, the quantity of foxes at any given time. So what it says is that the quantity of rabbits goes up and it goes down and it goes up and it goes down, and it repeats this through time. Okay, and similarly the population of wolves will go up and down through time, and so these oscillate in a relationship together. Okay, and even though it was very difficult to solve analytically, we're able to predict the long-term behavior of this anyway, which is very powerful. All right, let's have a look now at example 8.4. Consider the system x dash is minus x and y dash is minus 4x cubed plus y. Show that 0, 0 is the only equilibrium point or critical point. Well, that's easy here, because if we have a critical point, then the first equation must be equal to 0. So we must have x star equal to 0. All right, now if you back substitute into the second equation, x star equals 0, you get minus 4x star cubed is 0. And so you must have y star equal to 0. So the only critical point is 0, 0. Okay, so if we are to linearize this, we need to take the Jacobian matrix of this. We declare the first one to be lowercase f and the second one to be lowercase g, and we take partial derivatives. Okay, so I don't have a solution here. So this says try this on your own. Okay, so I'm just walking you through it then. I think I'll do question or example 8.5, even though it says try it on your own. Okay, so the next part of this says classify the linearized system and sketch it. Well, with that, what you would do is you take, after you linearize and sub in your 0, 0, you take the trace and the determinant of your matrix A, and you use that stability chart there in chapter 7 to classify what it is. Okay, and then finally, you can look at some particular cases, because this one you can solve the first equation separately, so you can actually solve this one. Now x dash equals minus x, that's separable and it's easy to separate. So you've got dy on x integrate equals the integral of minus 1 with respect to t. So you've got log of x is equal to minus t plus a constant, and then you write that as x equals a e to the minus t. Okay, so that's the general solution. And then next in question or part 5, use the general solution to find the general solution to the system. Okay, so this is a case where it's actually not too difficult to solve this system, because it's a fairly easy nonlinear system. So we have a solution for x, and it seems as though we can just back substitute that here. And then we have an equation that we can solve in y. Now it looks to be linear to me. Okay, so you would use the techniques for linear first order equations to solve the second one. All right, so that allows you to check. You can actually plot that particular, or the series of trajectories for various a values. And you can see how that works together with your classifying techniques, right? Of classifying the linearized system into the 6 main types. All right, now let's have a look at 8.5. It says when a nonlinear system depends on a parameter, then as the parameter changes, the equilibrium points can change. That is, as the parameter changes, a bifurcation can occur. Yeah, we call this a bifurcation when the parameter, say, drifts over time, right? So if you're modeling a system, now one comes to mind about cicadas in a forest and the cicadas eating pine trees. I surely have this wrong, but anyway, so parameters can drift over time, and then something unexpected can happen, and so you've got to go in and look at how your differential equation, how its critical points change with the drifting of the parameters, right? So you can lose a critical point altogether, for example. So that's what this exercise shows you. But you can actually study quite a lot on bifurcations. Okay, so let's have a look at the system and the problems we're going to do. So the first one, and I think I'll open up my window here so I can actually do these with you. Okay, show that for A negative, the system has no equilibrium points. All right, so we'll say if A is negative, then minus A is positive. So x squared minus A is always positive, and hence never equal to 0. All right, so that solves question 1 there. Next, show that for A positive, the system has 2 equilibrium points. Okay, so if A is positive, then when x dash equals 0, we have x squared minus A equals 0. So we can take the A over to the other side and then take square roots. So that says x squared is equal to A, and so x is equal to plus or minus the square root of A. All right, now if we back substitute that into the second equation, so since minus y x squared plus 1 equals 0, and we must have x equal to plus or minus the square root of A. Okay, then we can back substitute into this. So we have this, but we square that plus or minus root A, and we get just plain A. So we have this, but we know here that A is positive. So we say, and since A is positive, we must have y equal to 0. That's the only way you can get 0 out of that. Okay, so there are 2 critical points or equilibrium points. So we'll say hence we have exactly 2 critical points plus root A 0 and minus root A 0. Okay, so that completes the second one. All right, now let's have a look at when A is equal to 0. So if A is equal to 0, then what we have is the system x dash is equal to x squared, and y dash is equal to minus y x squared plus 1. Okay, so if x dash is 0, then clearly x is 0, right? That's the only solution for the first one. And y dash is 0, then has minus y 0 plus 1 equals 0, and so you see that y is equal to 0. Okay, so we have the unique critical point. Zero, zero in this case. All right, so there's only one. So that's number 3 done. Okay, final question says, find a linearization of the equilibrium point when a is 0 and compute the eigenvalues for this point. All right, so we're going to linearize this system here. So let's go ahead and set this as lowercase f and this one as lowercase g. All right, we need partial derivatives. So partial derivative of f with respect to x is just 2x. And the partial derivative of f with respect to y is 0, because there are no y's in it, and we treat x as a constant. The partial derivative of g with respect to x. Okay, so for this one, you might expand it first. You've got, you're differentiating minus x squared y minus y. So that is minus 2x, and then the derivative of minus y is 0 with respect to x. All right, so 2xy, right? Yeah, okay, minus 2xy. All right, so the partial derivative of g with respect to y is just the coefficient of y when we're treating the rest as constants, so we just have minus in brackets x squared plus 1. All right, so now we can calculate the Jacobian matrix at our unique critical point 0, 0. So we'll take all of these, put them in the right place first. And actually, let's set out another line here, right? So the Jacobian matrix is this, and then the Jacobian matrix at 0 is this. So 0, 0 minus 1. Okay, so very near that critical point, we have the linearized system. Y dash is 0, 0, 0 minus 1 times y. And then we don't need a plus b because our critical point is 0, 0. So we've got the linearized system near the equilibrium point when a is 0. Now we're going to compute the eigenvalues for this point. Okay, so the eigenvalues are solutions to det a minus lambda I equals 0. So if we put in minus lambdas here, lowercase lambda, where is that? Here, okay. And then here as well, equals 0. Okay, we take the determinant of this matrix and we get the product of these two. And so this is equal to 0, but I can, since they're two negatives, I can multiply those together and clear that and put a plus in here. All right, so this is our characteristic equation, and now we're solving this for lambda, so we get lambda is 0 and lambda is minus 1. Okay, so we've got the eigenvalues. So now let's classify what we've got here. We've got a negative trace and a 0 determinant. All right, so if we go back to, let's write this first. Okay, so trace of A is 0 and determinant, no, hang on, trace of A is minus 1. Trace of A is minus 1 and determinant of A is 0. Okay, let's go back to the stability chart. We said trace is negative and determinant is 0, so it's on the trace axis. So that says we've got 1, 0 eigenvalue, and so this is some kind of node, right, with a line of critical points, I believe. Okay, so that will be all for now. Next up, we're going to do Laplace transforms, and they're rather interesting because they give you a way to solve equations purely algebraically. Essentially, you transform to the Laplace domain, you solve some algebraic equations, and then you take the inverse Laplace transform and you get a solution to your differential equation. And you can also do it for systems. So that's coming up next.